Well, here's the theorem. Go ahead and write it down. Keeping in mind the hypothesis of the theorem is that f of x has to be continuous and differentiable. So continuous over the closed, differentiable over the open interval from a to b. Then here we have where calculus right there meets pre-calc, okay, or even algebra, because this is just the slope, the average rate of change over an interval, and then here we have the instantaneous. And keeping in mind, guys, calculus is talking about rates of change, and when we talk about a rate of change using calculus, we're talking about the rate of change at a moment in time. Kind of like when you drive your car and your average speed, let's say, is 70 miles an hour, then your instantaneous rate of change at somewhere along the way would be what the speedometer read at that moment, at a certain moment along the way. Okay, so that's it for that part, and let's go ahead and start doing some problems. So we're going to do two problems where we're answering all these questions about the function f of x, or in this case y. We're given the function y. We know that that's a polynomial function. So the first function that we're going to analyze is going to be polynomial, and the other one's going to be not a polynomial, in which you really have to, I just want to encourage you by saying this, you must make sure you understand the process, because on a polynomial function, we already know that the function is going to look like this. Okay, we already know that because of the negative in front of the x cubed. We know a cubic goes down from left to right based on our function aerobics and our understanding of polynomial functions. So it could have one critical point, in which we would have neither a max nor a min, or we could have two critical points, in which we'll have both a local min and a local max, but neither an absolute max nor an absolute min. So we already know what the function looks like, and keeping that in mind, we would have an inflection point also somewhere on the interior where it goes from, meaning the function f, or in this case y, goes from concave up to concave down, and which would be the case for both of these examples, concave up and then concave down. Okay, again, both of these examples, concave up and then concave down. So anyway, I want to start you off by analyzing a function whose shape that we know, and then apply that to a function whose shape we don't know. Okay? I wanted to pause here just to give you kind of a heads up on where we're going, though, and let's see if I can do this within the same video. Alright, I'm not sure how well you're going to be able to see what I drew, but anyway, we'll give it a shot. Okay, so here's the deal. We've got this function way up here, and we're going to be following this process of, and I'm hoping that you'll listen to this and watch this, because this visual might help you keep everything in order. Okay, because this is what sometimes you kind of get lost in the process of using the first and second derivative tests and what they mean and all that stuff. So we start with a function f of x. So if you could follow me along in this little graphic organizer, I just kind of was thinking, well, how can I really better help students understand the process here and to keep things in order? F of x is where we start. We always want to find the critical points, and so we come down here and we find f prime of x. We set f prime of x equal to 0, so we find critical points. So critical point number 1 would be where f prime is equal to 0. Okay, notice this line right here. That line right there is important because it's going to tell us something. And then coming down here, we see we find other critical points to the graph of f when f prime does not exist. Okay, and then we perform the f prime test to determine the intervals on which f prime is either positive or negative. Okay, so that's our f prime test. And then we come down here, and based on our f prime test, we know that when f prime is positive, we know that f is increasing. That's when f prime is positive. Okay, and then when f prime is negative, we know that f of x is decreasing. And we know that when f prime changes sign from f prime positive to f prime negative, that we have a max. And then when f prime changes sign from negative to positive, we have a min. Okay, well, let's look over here. We've got our second derivative test. In our second derivative test, we use that to determine the shape of the graph in terms of concavity, when f of x is concave up and concave down. And like I said, over to the left we had those straight lines, those diagonal lines. Well, over here to the right we have these kind of like these supporting, I don't know, I just thought, what kind of visual can I use to remind ourselves that the connection between f double prime and f is these guys right here. These guys, these are concave down or concave up. So f double prime, the second derivative of a function, always tells us the concavity of the function f. Okay, so f prime though, and these little diagonal lines, that tells us whether f is increasing or decreasing. Okay, so that we can't figure out whether f is increasing or decreasing by only looking at the second derivative. Okay, so keep that in mind, that the second derivative test we find when f double prime is equal to 0 or when f double prime does not exist. Okay, f double prime does not exist. And then from that we make a sign chart, and then from the sign chart we can determine the sign of f double prime, which would tell us when f is concave up. So if f double prime is positive, and I know we covered this before in the most recent lesson, but f double prime being negative is when f is concave down. So keep in mind the shape of f is determined by f double prime concave up or down. Inflection points are when we have a point on the curve where it's continuous there, but also we have a change in concavity from down to up or from up to down. Okay? And that's the general kind of format that we're going to follow if we want to use our first and second derivative tests to analyze the graph of the function. Okay, so keep that in mind, and then we'll get started. And back to our example. So again, we want to find y prime. Y prime is negative 6, I almost put 8. 3 times 2 is 6, x squared, plus the derivative of 6x squared is 12x. And at the same time, I'm going to go ahead and find y double prime. Y double prime is negative 12x plus 12. Okay, well, the first derivative test, y prime equals 0. Let's try that right down here. Y prime equals 0 when negative 6x squared, negative 6x squared plus 12x is equal to 0. If we factor out a negative 6x, we see that we get x minus 2 is equal to 0 as well. And then we know that if negative 6x is equal to 0, x has to be 0 or x has to be 2. So these are the two critical points. Critical points. Okay? And those are our only two critical points because we know that we have a polynomial function. The derivative exists everywhere, so y prime does not exist will not lead any yield any critical points. And then we're going to take our second derivative and set it equal to 0. Y double prime is equal to 0 when, I should have put the word when here, when negative 12x plus 12 is equal to 0. Hopefully we can see, factor out a negative 12, and we get x minus 1 equals 0. Either way, we get x equals 1. That's our only critical point for y double prime. Okay. Let's see here. I'm going to need some room. So do me a favor, write this down. We have critical points. Okay, just write that stuff down, and then I need to erase the screen. No, I'll just do that. I'll just erase what I don't need. Okay. So we've got all that, and we need our y prime test, and we make a little make a little number line here, and we put our two critical points, which were 0 and 2. Okay, so the sign of y prime is going to determine whether or not, for each of these intervals, whether y prime is positive or negative. So we know that when you see y prime, and I should have left y prime up there, that was stupid, sorry. Y prime is negative 6x squared plus 12x. Having it factored is easier. Negative 6x times x minus 2. X minus 2, yeah. And so to the left of 0, if x is negative, then we have a negative times a negative, and then negative times a negative times a negative. Okay? So that means that on that interval, from negative infinity to 0, y prime is negative. Okay? Meanwhile, y prime on the interval from 0 to 2, we see we have negative 6 multiplied by x, which is, let's say, some test value of 1, which is positive. 1 minus 2 is going to be negative. So therefore, on the interval from 0 to 2, y prime is positive. Okay? Well, then on the interval from 2 to infinity, we can see we have a negative 6 times a positive times a positive. Therefore, on the interval from 2 to infinity, we've got f prime being, or y prime being negative. Okay? So from that information, we can go ahead and answer the questions here, back up here at the top. Y prime is, y is increasing on the interval from 0 to 2, because y prime is positive on that interval. Y is decreasing on the interval from negative infinity to 0, and also on the interval from 2 to infinity, because y prime is negative on that interval. Okay? And what I like to do is, in my sign chart, I like to draw the shape of the graph, because I know that the shape of the graph is going to help me visually. But if y prime is negative, let me erase these guys here. Oh, wow, that's a big eraser. Put those back. Smaller eraser. And we're going to erase these guys because I want to draw the shape of the graph. Okay, so the shape of the graph of y, if y prime is negative, we know that y is decreasing. And then if y prime is positive, we know y is increasing. And here, y prime negative, decreasing again. So when x is equal to 0, guess what? We've got a min. Okay, so we have a min here because y prime changes from negative to positive there, and we have a max right there when x is equal to 2. So local extreme values, when we can say over here to the left, when x is equal to 0, we have a min, and when x is equal to 2, we have a max. Okay? So those are our local, those are where our local extreme values occur. We could find the y values by plugging those values into the original equation. But now, again, we've got y double prime. We're going to try to figure out when y is concave up and concave down, and also where y might have an inflection point. Okay, so let's write down our y double prime again. It's negative 12x plus 12. Okay, and then we remembered that when x is equal to 1, we have a critical point of y double prime. So we factor out a negative 12 and get x minus 1. So pretty quickly, though, we could determine the sign of y double prime. To the left of 1, we could just pick a test value of 0. The first term here is going to be negative, but 0 minus 1 is also negative. So therefore, a negative times a negative is a positive. And we know, though, that y double prime being positive means that y is concave up. Positive, we're happy. Concave up looks like a cup, looks like a smile. And to the right of 1, we can plug in any test value. Let's say we plug in 10. The first term, negative 12, that's always going to be negative. 10 minus 1 is going to be positive. So therefore, to the right of 1, to the right of this critical point for f double prime, our y double prime, I should say, is negative. And so we know that negative means that y is concave down, and so therefore we have our intervals for concave up and concave down. Concave up would be from negative infinity to 1, negative infinity to 1, and then concave down would be from 1 to infinity. We know that y is defined at 1, it's continuous, so our inflection points are going to occur. There's only one of them where y changes concavity at x equals 1, so there's where we have our inflection point. In the next video, I'm going to show you what the graph should look like.